Good morning and welcome to the session number 2 for Virtual Check 2020. My name is John Garfola. I'm an information security analyst at Emporia State University. And for session 2, you're tuning into a presentation about how to provide high availability for Fort Hays State University authentication services, a unique approach to the subject. With us today, we've got Aaron, Livy, and Greg, and they're going to be discussing some of the challenges and ways that they overcame moving to a hybrid environment. And don't forget to submit questions in the chat. A link will be posted if you're watching this live in the YouTube channel. Without further ado, Aaron, Livy, and Greg.
Good morning, and thanks for joining us. Today we're going to talk about how we set out to provide high availability for our authentication services at Fort Hays State University. I'm Aaron Rowe, Server Operations Manager at Fort Hays, and joining me on the presentation today are Greg Grayman and Livy Lee, two of the talented systems administrators I have on my team. So I know you're probably wondering, well, what's so unique about our approach? We evaluated and experimented with several different methods and architectures, and we'll talk about those in more detail later in the presentation. Since we primarily use ADFS, the typical recommendation we saw was to use standard Microsoft solutions like Network Load Balancer and Web Application Proxies. These didn't work well in our testing, particularly during failover and failback, and had some limitations when trying to implement a fully HA solution across at least 2 sites, so we decided not to use this recommended architecture. The hybrid approach that we arrived at leverages a combination of Microsoft technologies, open source projects utilizing both on-premise servers, servers in an off-site location, as well as cloud technologies to provide our resilient HA service. We felt like the combination of all this was a pretty unique approach, and I hope you do as well. Before we get into the nitty-gritty details about our solution, in order to understand some of our design decisions, it may help to provide a little background about our environment. A number of years ago, our student identities and our faculty and staff identities were housed in 2 separate directories: Tivoli Directory Server for students and AD for faculty and staff. We had CAS to provide single sign-on for numerous in-house and third-party applications, and we used IBM Notes for workflow and email. Then along came Office 365. Administration at the time made the decision to migrate from Lotus Notes to Exchange Online for email, and provide our students with the Office 365 suite to leverage the student use benefit that comes with our campus agreement. In order to accomplish this, we partnered with a vendor to help migrate all student accounts from Tivoli into AD, configure ADFS for single sign-on, and migrate our email. Since we already had CAS, at first the only relying party that used ADFS was Office 365. Naturally though, once ADFS was implemented, we began finding more and more services to integrate with it, so our dependence on ADFS began to grow.
At this point in time, this is what our authentication architecture looked like. To keep cost and complexity down, the vendor recommended a simple DNS round robin for the initial ADFS deployment. It worked, but it definitely wasn't ideal. Our authentication systems were all on campus, and that seemed fine when all of our systems were on campus as well. But with the extension of our systems to include cloud infrastructure and the rise of importance regarding disaster recovery and business continuity, we needed our authentication systems to be capable of working in the event of disrupted connectivity, a service outage on campus, or a full-on disaster. This need was highlighted not only by the K-State fire we're all familiar with, but also by a couple of unanticipated internet outages on campus. While we had an off-site backup location, it wasn't something we could use in a disaster recovery or business continuity event. Our site was a building across town that relied on a connection back to our main campus for connectivity. Another need for change was that some of our systems used CAS and others used ADFS, and the login experience was inconsistent.
So we set out to come up with a solution that solved all these problems. As I mentioned before, we evaluated a number of different options, including running our own domain controllers and authentication servers either partially or entirely in the cloud, load balancer services such as Total Uptime among others, and cloud load balancer options such as AWS Elastic Load Balancing, Azure Load Balancer, and Google Cloud Load Balancing. In addition to the fact that not all of these options even had the ability to do hybrid load balancing, that is, balance between both the cloud and on-premise, there were also licensing issues for Windows licenses. At the time of our evaluation, only Azure allowed us to bring our own licenses, meaning that we would be paying more for licensing to run our servers in either AWS or Google Cloud. To round out our evaluation, our CIO also reached out to other universities to inquire about co-location options.
While evaluating our potential solutions, something became obvious. The solutions available in the open market were priced according to what resources most entities have available to them, but we have resources that most businesses don't. Locations willing to provide us space for next to nothing and a big fat pipe to them. Thanks to Wichita State offering us rack space and our CAN-RAN connection straight to them, we have access to colo space for next to nothing. That's hard for other options on the market to compete with. Not only would utilizing this resource allow us to spread our authentication infrastructure outside of our local campus, it provides an off-site disaster recovery business continuity site that can be utilized without dependence on our main campus. Since we had some old servers that we were taking out of service, we had the hardware needed to implement a proof of concept cheaply and easily. Our solution is a hybrid of on-premise, off-site data center at Wichita State and the cloud with Google Cloud Platform. As we started to utilize the server space at Wichita State University for our backups, we also brought over 2 of our previously decommissioned physical servers. Using those 2 servers, we stood up 2 ESXi hosts. We then set up Active Directory domain controllers on each of them, and then created ADFS servers on each of them as well on a private network. On a public network, we initially wanted to have the similar setup to what we had on-premise. That is, to install 2 web application proxy servers on them, then use DNS round robin for the traffic. But the problem is, 2 ESXi hosts as a proof of concept there do not have any shared storage, and we really do not have an HA environment. DNS round robin would not work well for us because it is possible DNS would resolve to an IP that is currently down at any given time, and then result in service interruption. So, we ended up with 2 HA proxy servers with floating IPs using VRRP and KeepLiveD. That at least gave us some kind of HA on our WSU cluster for ADFS. Then the question becomes, what do we do with the adfs.fhsu.edu domain name? We had to use some kind of load balancer. The question is where to put it.
As we evaluated all the options that Aaron mentioned in an earlier slide, we decided to set up an HA proxy server on Google Cloud using the $300 trial credits that they had available to us. And we know if this works out well, we'll have other similar services that we would like to run just like this. The first thing that jumps to mind is to use Compute Engine in Google Cloud to create 1 VM per each service, right? Because that is what we are familiar with, and that is what we do every day, creating VMs in a virtual environment and manage them. However, it would not be ideal for a few reasons. Since they are single VMs, there's still single point of failure. We'll have to update them, apply patches, and other maintenance jobs that may require downtime. It will be very hard to scale them if we need them to. And it really doesn't make sense money-wise to create additional VMs for each additional service. We ended up using Google Kubernetes engine and created a 3-node multi-zonal cluster that spans across 3 different zones. GKE takes care of upgrading and maintenance of the nodes for us and offered a true HA environment. We just run our Dockerized container on GKE. With their horizontal pod auto-scaling, we are able to set up auto-scaling policy depending on different metrics, such as CPU utilization. We Dockerized our ADFS HA proxy server and set up a workload or a pod on GKE, then created a service and ingress for the adfs.fhsu.edu domain name. Using the horizontal pod auto-scaling, we were able to set up the pod to auto-scale if the CPU reaches 80%. Our initial setup ended up with this. And to be honest, we joke among ourselves that this is a pyramid of load balancers. And most of the load balancers are HA proxy servers, but there's the default ingress load balancer on GKE as well. Later, we found we had some issues with this setup, and we'll talk about that in detail later in the presentation. Now that we have taken care of the ADFS server, what about CAS? As Aaron mentioned earlier, CAS is also using Active Directory as backend. So initially, we want just to copy what we did here for ADFS, right? One server on-prem, one server at Wichita State, and then load balancer on GKE. However, issues with that, CAS operates differently with ADFS. For a CAS cluster to work, they will need to have a central ticket storage. But we were fortunate enough to get by with just one single CAS server, because according to the CAS documentation, if you have a sophisticated virtual environment that handles HA well, a single node CAS is sufficient. So we didn't want to over-engineer this part too, as we were kind of phasing out CAS in favor of ADFS whenever we can. We Dockerized the CAS server as well and set up a pod on GKE and configured CAS as a relying party trust on ADFS. As a result, whenever a user accesses CAS, they are redirected automatically to ADFS for authentication. The added benefit for this is CAS becomes transparent for users. They don't even know they hit CAS first. That way allows us to have a unified login experience and better SSO. In terms of multi-factor authentication, we just needed to configure Duo on ADFS alone and do not need to configure it on CAS. This is what our setup looked like after CAS. We were pretty happy with this setup for a little while, but then we faced some issues. We will talk about those issues in a later section, but primarily, there are just way too many proxies and load balancers. Right? The two web application proxies, the two HA proxy at WSU for our budget HA, and the auto-scaling HA proxy pods, and the load balancer on GKE. Fast forward a little bit, we eventually get rid of the pyramids of load balancers setup and just use the port forwarding on the border firewall so that HA proxy pods on GKE can talk directly to the ADFS servers on our private network. HA proxy pods on GKE serves as a load balancer for the 4 different ADFS servers, 2 on-prem and 2 at Wichita State. We configured HA proxy pods on GKE to constantly perform layer 7 health checks on the 4 ADFS servers, making sure all of them are available to respond to the requests. We currently set the server weight to 70% on-prem and 30% on WSU. Let's walk through the whole process in the scenario. Let's say if a user accesses one of our web services, whether it's in the cloud or on-prem. For example, in this case, a user wants to access Blackboard. As we configure Blackboard to use CAS for authentication, the Blackboard redirects the user to CAS. When a web browser makes a request to cas.fhsu.edu, the DNS name resolves to an ingress IP address on GKE. GKE then passes the request to a pod running our CAS server. As we mentioned, CAS is configured as a relying party on ADFS. CAS then issues the redirects to ADFS. Browser then makes the request to adfs.fhsu.edu, and the DNS name resolves to a different IP address on the ADFS ingress interface. Then the request passes through to one of the auto-scaled pod running HA proxy. HA proxy as a load balancer decides which ADFS server the request goes to. Finally, after all these processes, a login window finally appears in the user's browser, waiting for the username and password to be entered. Problems and issues. The first issue that we encountered when we were trying to deploy this method is the different new technologies that we are facing: Kubernetes, Docker, and cloud. Nobody on our team had any experience dealing with the new technologies like this. So there are a lot of things to learn in a very short amount of time. Also in GCP, the price is not fixed. It's more like a pay-as-you-go approach. There was some adjusting on our end for that as well. Another issue that we encountered was logging. Well, not that kind of logging. Yes, logging. We have to rely heavily on Stackdriver, which they later rebranded as Cloud Logging. But personally, I really miss the ease of use of the command line tools, where I can just simply type a command and expect the result to be returned. And then I can also pipe several commands together to easily get what I want quickly. As a Linux user myself, I'm not a big fan of using mouse to click around, but still able to do that kind of by directly running commands on the live pod using kubectl command. But you'd have to know what pod to run that command on, because of the auto scaling. There could be a number of different pods running at a given time. I have to point out, however, the cloud logging does provide some Python tool that allows us to run command directly to interact with cloud logging, but I really haven't mastered that yet. More things to learn.
Another issue we encountered with logging is passing the real client IP address to the ADFS servers. As Livia mentioned earlier, we had that pyramid of load balancers, a whole bunch of HA proxies at different levels. And at first we decided to use TCP mode for the HA proxy servers, because if we were to use HTTP mode, it's kind of a pain to manage so many different HTTPS certificates on each one. As a result of the TCP mode, we could not perform any HTTP header manipulation. However, that resulted in ADFS servers just logging the last load balancer's IP as the source address. After our decision to get rid of the unnecessary load balancers in between and just use port forwarding on the border firewall, we essentially just need to manage one HA proxy Docker image, so we were able to do SSL termination more easily. By doing that, we were also able to insert the necessary HTTP headers for the ADFS servers to record the real source IP addresses in the security event log. You can see from the screenshot here the additional headers listed. However, we also use Manage Engine's AD Audit Plus for Active Directory audit logging and reports, and it also supports ingesting ADFS logs. It's very handy in particular to determine where an authentication failure is originating. If perhaps someone changes their password but a device has credentials stored, AD Audit makes it easier to track that down. In the default configuration, however, AD Audit did not parse those additional headers that we've inserted in the logs. We had to engage their support, and they've been very helpful, made some changes to our AD Audit instance and database tables, and eventually was able to get that issue fixed for us. There was also a minor change that we had to do on the GKE ingress as well. Otherwise, the GKE's IP address would show up everywhere instead of the real client IPs. That was a minor change and really painless to implement. You can see in the screenshot here the external traffic policy value is set to local. This forces the proxy to only proxy requests to local endpoints and does not forward traffic to other nodes, preserving the original source IP. You can find more information about this behavior in the Kubernetes documentation. So what did all this cost? As we moved through this project, we did our best to continually evaluate all the costs involved to determine our best option when all aspects are taken into consideration. This included capital expenses, licensing, usage fees, bandwidth costs, etc. Some methods were heavy on capital costs, some were heavy on operating costs. Once we had made the decision to partner with Wichita State for our backup site, we began developing our proof of concept, refining that design, and eliminating unnecessary complexities and cost wherever we could. What we ended up with, we felt like, was a pretty good balance between capital and operating expenses. Our capital expenses were minimal. We had to buy the rack hardware, including PDUs and a KVM to match the standards that WSU already had in place, and some network and firewall hardware and licensing. And we would have had to buy server hardware had we not already had some that we could use for our proof of concept. Eventually, we will incur some additional costs as we get better equipment to service our future disaster recovery and business continuity plans. And we have some additional operating costs as well, such as Windows and VMware licensing, Google Cloud usage fees, which have averaged about $200 per month over the last 12 months, and travel costs to the colo to perform maintenance or service. Obviously, a purely cloud solution would not have had these travel costs. However, given the advantages, we felt like it was an acceptable compromise. I'll also note that the way this is structured, we can add as many additional services to our 3-node GKE cluster as we want without any increase in cost. The only increase in cost would come from the autoscaling in the event of high load that Livy mentioned earlier. So while our Google Cloud costs are technically variable, we're confident that these costs are going to remain relatively stable.
So, you can see that by leveraging our partnership with Wichita State University and cloud technologies, we have a robust HA authentication system. But more than that, we've laid the foundation for extending our infrastructure beyond our campus in a resilient fashion. We expect to be adding additional resources to our extended network to further ensure stability and seamless high availability to those that rely on us. In fact, we have already put one of our web servers there behind a load balancer, ensuring that our main website can be reached even if our main campus goes offline. We're currently in the planning stage of putting additional monitoring that will monitor our Wichita State resources as well as the off-campus availability of our main campus from off-site. Thanks for watching our presentation. We look forward to answering any questions you might have. Stick around for a live Q&A or feel free to reach out to us via email at check2020@fhsu.edu.
Go. All right, everybody, thank you for attending this virtual check seminar. And if you're anything like me, I think you're probably saying, wow, this is truly an impressive presentation to highlight a lot of the ways that hybrid authentication can really bring a lot of value to an organization. And one quick question for you. Kind of how did this all come about? How did the change occur? And were there any buy-in hurdles you had to deal with?
Yeah, so again, yeah, thanks for everybody joining the presentation and watching. Glad we could be here. Really, we didn't have a lot of challenges with buy-in, especially after the check conference that we had that immediately was at the same time as the Hill library fire. We attended that check. There was a lot of conversation about the challenges that they had faced because of their authentication being in basically the exact same scenario as we had. And we knew that that was a problem, and that if we had an outage or a disaster, that we would be scrambling. We kind of knew that. It just never was made a priority. So after all of the conversation and the things that we talked about as a result of that disaster, we really our CIO said, hey, we know that we're in the same boat, and we can fix it ahead of time, so that if we do have a problem, we're not scrambling. Can we just go ahead and make that a priority? So kind of, I guess, thanks to Check and to that disaster and the collaboration that we have there, it really kind of pushed that forward and made us realize that we needed to make it a bigger priority.
Right on, Aaron. It sounds like that's exactly your use case is exactly what occurred because of the Czech conference, and I think that that's something that everybody can take away from this is that networking capability and finding out how others are doing it. I think it's fantastic, and I look forward to maybe arranging a trip to see you guys myself. So, are there any other clarifications or parting shots before we close up?
I guess I could only say one thing. Talked a little bit about the costs and the auto scaling in the presentation, and there was a minor, I guess, correction that I have there. I talked about the auto scaling for CPU utilization. So the auto scaling would actually auto scale the pods inside of the 3-node cluster. So the auto scaling in itself would not necessarily create an increase in cost. That increase in cost would only come about if we added so many more services, or we had such an increase in that scale that we needed to add another host or another node to our Kubernetes cluster. So just the auto scaling of the pods would not necessarily increase the cost. Another minor clarification is there is a minor cost for each additional public IP. I said that we wouldn't have any increased in cost for additional services. That's not entirely true. We would have to pay for an additional IP per every service that we added, but that cost is pretty minimal in the grand scheme of things. So that's the only clarification that I had.
Okay, fantastic. Thank you again, Aaron,
Greg,
and Livy. And thank you for watching. We hope you'll attend some of the future sessions today. And please feel free. We'll have all of these sessions available recorded for future reference. We hope we'll see you again. Take care.
Thanks, John.